So this program is called Learning with Less Labels. Before you tell me that this title is ungrammatical, I know, and maybe it should be something more like Learning with Less Labeling or Learning with Fewer Labels. But none of those things quite has the flavor of what I'm looking for here. So we chose Learning with Less Labels, or as it's pronounced, LwLL. So just so that you have a sense of what we're looking for. The goal of this program is to create machine learning algorithms that can learn with 10 to the 6th x less labels than what we use today, and to adapt to new environments with less than hundreds of labels. These are soft numbers, and we'll talk a little bit more about the objectives in more formal terms when we get to the metrics portion of this presentation. The other aspect of this program is to build a theoretical foundation for understanding the theoretical limits of learning and adaptation given tasks and data in the presence of things like transfer learning, like meta-learning, like transfer meta-learning, like reinforcement learning, and so on. So we want to have a more deeply articulated and useful theory that predicts these limits and predicts bounds that are as tight as possible so that we can actually do something with them. So as many of you know, we have theory today, but that theory is often not empirically very useful for many of the problems that we care about. Okay. Just to briefly caricaturize the labeling problem, as many of you know, the way that machine learning has evolved over the last couple of years, we have systems that essentially can continue to learn in the presence of more and more data. A lot of the innovation that has happened in terms of empirical results have been machine learning systems that can really capitalize on the use of more and more data, namely deep neural networks. So when we look at tasks like object recognition, speech recognition, translation, it is very typical these days to have data sets with labels associated with those data sets on the order of 10 to the 9th, 10 to the 8th, 10 to the 10th labeled data elements per training set. Now, that gives us really great performance. And one of the things that we have learned over this over the last 30 years is that in order to get incrementally linear gains, we typically have to multiply our data sets in terms of size. So you'll notice the log linear scale of this plot. This is for a task that I worked on for many years, machine translation. But this kind of learning curve basically exists in all domains that we typically apply these kinds of techniques to. Now, despite the fact that we can make use of this amount of data and that we can get good accuracies using these kinds of models, we have various problems associated with the models that we actually build, not the least of which is domain change. So we, on the government side, witness this all the time. There are many people in this room that have worked on government problems or our government. We have all experienced the various forms of catastrophic failure associated with taking models that are trained on crowdsourced labels, open imagery, open text, open speech, to only get catastrophic failure when we actually try to deploy these things in real life, largely because of some kind of mismatch in the domain, some kind of variable that has changed that we often cannot clearly articulate upfront what it is. Now, the solution that we have tried to undertake in various DARPA programs, various research efforts, and operational deployments has been to create new labeled data sets for those environments and domains that we care about. And unfortunately for us in the government, we have a particular problem, which is that when we have data that's highly protected, and this is also true of corporate environments where the data is proprietary, we end up not being able to reveal that data, and the result of that is that the cheap labor source that we have through crowdsourcing isn't available to us. Just to give you a sense of how stark the contrast is between what people who can use crowdsourcing can pay versus what we have to pay. You can take a look at the table here. Basically, the net result of this is that we pay lots more money in order to get data sets of similar size, or we don't create data sets of those sizes, or we wait a long time, and we wait a long time generally in order to be able to achieve that because we don't have the labor pools that are available to us. Okay. Then to make matters worse, generally when we deploy these models, we have a continuous labeling need or a continuous retraining need. There's efforts to think about how to solve that, but basically when we try to deploy these systems in new environments, we end up with yet again the domain mismatch problem. So it's sort of a continuous cycle of continuing to need labels. This situation is both expensive and not very feasible for many applications, especially for applications where crowdsourcing isn't available to us. So what we want to do in this program is to get out of this paradigm. And the paradigm is basically we need a lot of labeled data to learn. We are generally unable to adapt in unsupervised ways, meaning that when we have no labeled data, we can't really make use of that in a useful way. In other words, we have data, but we don't have the labels associated with it. There's limited amount of efficacy to the methods that we have to improve our systems. And this is despite lots and lots of hard work in unsupervised learning. It's not that people haven't tried, it's that it's a hard problem. The other alternative when we go to deploy systems is we can do this, right? We can essentially have more data, more labeled data in a new domain that we care about, but the amount of savings that we get in a new domain is generally not very much. In other words, maybe we can reduce the amount of data we need by an order of magnitude or two, but we're still talking about 10 to the 6th, 10 to the 7th in terms of the amount of data that we need to build models. So what we want to get to in this program is a capability to build models with much less labeled data, or much fewer labels in our data, if you want to be grammatically correct about it. And we think that you can do this by one, making use of the labeled data that you have in smarter ways, and two, finding better ways to make use of the unlabeled data that we have available to us. The assumption in this program is that unlabeled data is essentially free, that labeled data is costly, and the question is, what can you do with the data that's effectively free for you? What can you do with a small amount of the data that is expensive? So we want to get to a point where we have very few labels to train initial models and very few labels to adapt to new domains, and we have mechanisms that make use of unlabeled data in efficient ways to improve accuracy and achieve similar to current state-of-the-art accuracy, but with 10 to the 6x less labeled data to train initial models. Okay. So why do we think this is possible? We think this is possible because there are problems with how we actually do machine learning today. So I'm going to give you a sort of cartoon sketch, and those of you that are experts in the room, I apologize for the cartoonish nature of the problem. But really, it is generally true that almost all of our machine learning algorithms boil down to some kind of optimization problem, some kind of optimization where you try to find a set of weights or a model that minimizes some kind of empirical loss. And this particular empirical loss function is basically what you would see for a one-layer neural network without any nonlinearity, with a square loss function. And that scenario relies on a number of things, right? The first thing that it relies on is the fact that n is large. And it is important here that n is large in this particular equation because we generally don't come with idealized observations, right? We assume that our observations include some kind of noise component to them. And the way that we eliminate this noise and focus on the underlying idealized observation is through averaging, essentially. And the opportunity here is to try to think a little bit about better ways to eliminate these kinds of nuisance variables, right? It's still the case that even with large n, like 10 to the 9th, 10 to the 10th n, right, we still have problems eliminating nuisances, right? So all you need to see are the various ways in which our systems fail when you deploy them, whether they're ImageNet systems, translation systems, and so on. They still make obviously wrong answers, and obviously part of the problem in these systems is that they're not focusing on exactly the right things. So how can we find a better way to eliminate these kinds of nuisances, transform our data into something that actually is more relevant in the process of doing so. This is a key challenge for this particular program. Now, the other problem with this formulation of machine learning is that you notice here that every time there's an X, there's a Y. Every time there's an X, there's a Y. That basically means you need labeled data. And this one-to-one correspondence, while this is not the only way to do learning, is a very typical way to do learning. And what that results in is that we don't really have a great way in this formulation, especially this optimization formulation, to take advantage of the unlabeled data that's available to us. So again, the premise behind this program is that we have this finite but expensive set, and that is true for many, many problems and many, many operating scenarios where we want to deploy machine learning systems. But we generally also have this huge pile of unlabeled data available to us. So we could probably have an infinite supply of that, but we don't know what to do with it in an effective way. So what we would like to do in this program is to automatically find ways to generalize these kinds of learning objectives that take advantage of the ability to make use of this kind of unlabeled data, that learn how to remove nuisance as part of the learning objective. And then also we would like to be able to prove limits on how far we can actually take this. So I've set a set of objectives for problems that, that I know about where I think we can achieve reductions of the order of million X. But not all problems are going to be the same. Right? Some problems are more complex than others. Some learning problems will require more labeled data than others because they're trying to make more predictions or trying to make less predictions, etc. And so one of the things we want to understand in this program is what the fundamental limits are for a given problem in terms of learning given the number of labels that are going to be needed. In other words, what is the minimum number of labels we would need for a given problem in the presence of things like transfer learning and other things that we can do today. Okay. So the program is divided into two technical areas. I'm going to go into each of these technical areas very briefly. These slides tell you a little bit about what I hypothesize might matter in these two technical areas. But that doesn't mean that that should limit you in terms of thinking about what you think might matter. So you will necessarily have different hypotheses than I do about how to fix this problem. I care about the problem. I care less about my particular hypotheses to the solution. This is a fundamental research program, so you will have different approaches than the ones that I'm thinking about, and that's okay. In fact, I invite you to propose those differing approaches. The first technical area, I'm going to divide this into two parts. The first part is figuring out what matters here. One approach that I have in mind for doing this is to look at meta transfer learning as a potential avenue for better information into how we determine what really matters in our observations. Okay, so if the goal here is to figure out what our underlying observations really should be, i.e. what we should be caring about when we look at the data that we're trying to make predictions about. One way to do that is to look at problems that are related to the problem at hand. Look at other data sets that we've already built models for and understand what's similar between these problems so that we can eliminate variances across data sets that are likely to be nuisance variations. Now, the key assumption under the hood here is that all of our data collections have some bias associated with them, but probably across data sets there are different biases associated with each of these data sets, and looking across data sets allows you to remove bias in a way that you couldn't do by looking at an individual data set. In other words, you don't necessarily have enough information to understand the bias that you have from an individual collection, especially if that collection is static and upfront. So if you think about what that means for a moment, what we're essentially saying here is that this kind of bias removal, coupled with transfer learning techniques to find related problems, can help you figure out what matters. Earlier, I mean at the time of labeling. So if you have a data collection process, and you label that data, you're kind of stuck with the subset that you've chosen up front, and then unlearning the biases associated with that may be a hard task. So another way to do this would be to automatically figure out what you should be looking at. In other words, have a machine learning system that helps guide the examples that you actually label. Now, of course, this is typically called active learning. And a class of these techniques has been developed over the last couple of years. We're going to support methods of active learning here that improve on our current state of the art. And what we really care about here is being able to figure out how to perform optimal experimentation here, right? So the idea is to turn the active learning problem into an automated experiment design problem so that we can then actually run a series of controlled experiments with labeling in the loop to determine the factors that matter versus the factors that don't. Okay, so I also mentioned that a secondary objective in this technical area is figuring out how to deal with this unlabeled data. Now, many of you know about the existing unsupervised methods for doing this. I'm not going to get into too many of the details here, but there certainly could be approaches that are better at moving distributional shift and changing the statistical dynamics of an observed set relative to its difference with some kind of training set. Those kinds of approaches have been explored for many decades, but I think there are possibly novel approaches in this area that do more than that. So one class of approaches are approaches that turn problems that have some kind of explicit labeling requirement into problems that only require a correlated reward signal. So if you can turn problems that are essentially supervised learning problems into reinforcement learning problems, then you have a signal by which you can get supervision effectively for free. The example I'm showing you here is something that was done manually in a paper recently. And the basic concept here was to take an object recognition system, embed it into a robot navigation task, and that robot navigation task essentially could be used to improve the object recognition system because this implicit reward signal of being able to avoid objects was used to essentially optimize the overall system. Now, that kind of problem, that kind of solution was done manually by somebody noticing that these two problems were related to each other and then doing this embedding in a manual way. We want to find automated ways to do this. In other words, how can you find that a problem has a correlated reward associated with it potentially that would allow you to automatically determine a set of embeddings that would allow you to push a problem like object detection into a robot navigation problem. Another variant of this kind of work has been work that Stanford has done on creating models that generate proxy labels that allow you to then learn with noisy supervision. And that's, that kind of approach has the advantage that, or takes advantage of the fact that certain kinds of learning algorithms are more efficient, but possibly less accurate in their end state than other classes of algorithms, and using them to co-learn and bootstrap is a potential source of being able to create efficiencies in our learning processes. So these are just examples of approaches that could be used here. I've highlighted a couple of these that I think are novel, but there are potentially many others that are very novel. And the call for you guys to think about is, what is your novel approach here? When we get to the problem formulation here in terms of how we challenge you in this program, you'll understand that there are no guardrails on what you do here other than the prescription of how these challenge problems are set up. And they're very flexible for you to be able to express other ideas here that are your own. Okay, so the second technical area of this program has to do with the theoretical limits. Okay, there are a series of key questions here that we care about. One, we would like to be able to understand how hard a classification problem really is. There have been theoretical approaches to this. If you think about sort of characterizing problems in terms of their VC dimension, characterizing decision boundaries, and so on. We would like to be able to have a way, given a problem, and given the presence of a bunch of other learning scenarios, to be able to characterize a problem, both in terms of its true classification rank, but also in terms of its data complexity. Because as we know, these two things are intimately related to each other, and typically the theory tells us something about the data or something about the classification problem, but not jointly anything about both of them simultaneously. And we would like to have a better understanding of what those are. We would also like to have an understanding of how discoverable these true characterizations are. In other words, in all learning problems, we have a finite sample of the data that we actually have. We generally have a biased sample of the data that is actually out there for the problem that we have. Given that sample, given that bias, how likely is it that we can recover the true rank of the problem? How likely is it that we can determine what a good model is or an optimal model is? How likely is it that we can recover that optimal model? These are the kinds of questions we would like to solve. And if we break this down at a high level, this is a very theoretical, technical area, so if we break this down at a high level, we want to have a way to formally characterize problem complexity. We want to have a way to formally characterize things like domain mismatch, because we'd like to be able to understand this in the presence of training and in the presence of adaptation. So given a new domain, how hard will that new domain be to adapt to? We would like to prove complexity and transfer limits for these problem classes and domain mismatches given a measure of domain mismatch. And we'd like to be able to understand things like, for instance, how much data we actually need, examples we need to be able to recover the underlying models for a given accuracy that we care about. Okay, so the critical bit of these two technical areas is this, how we design our evaluations. So for the first technical area, there is an evaluation, for both technical areas really, there is an evaluation that we design every 12 months during this program. I should mention that this is a 3-year program. I'll show you a schedule associated with this in a couple of minutes. But this is a 3-year program where each of the years of the program ends with a challenge problem evaluation. So you will be presented with a new challenge problem, and that challenge problem will be across multiple different kinds of tasks, multiple different kinds of data modalities, and it will involve 2 subtasks for you guys, for your systems, for your algorithms. First is the ability to train a new model from scratch. And the second is to be able to adapt that model to a new domain. So for every one of these challenge problems, we define an initial domain, and then we define a transfer or adaptation domain for you to work on. So you need to work on both sets of that problem. When you do this, we will gradually decrease the amount of labeled data that's available to you, ending with thousands of labeled examples by the end of the program. Starting with sort of small millions of examples in the first phase of this program, or the first of these evaluations. And an important aspect of this design, evaluation design, is that you will have the ability to ask for the data that you get labeled. Okay? So I mentioned to you that we want you to be able to do active learning if that is the approach that you want to take. And what that means for us is that we are essentially taking a larger pool of data that has been labeled, and then you have the ability to ask for the specific subset that you want labeled for training purposes and for adaptation purposes. On the TA2 side of this, on the theoretical side of this, we want you to apply your theory. So these evaluations are now not about building the model, but about applying the theory. And your theory is going to make a series of predictions about the bounds of these learning problems. Now, it's bad if the empirical people beat your bounds, right? If they beat your bounds, something is wrong with your theory. And so we would like to have a back and forth, a sort of adversarial back and forth between you. And that's essentially the design of these evaluations. Now, I mentioned that we have a series of goals for this, this task. I have not revealed to you the underlying adaptation tasks. So they're all listed as TBD, and the actual data sets here may change. But these are well-known problems that I think most of you have had some experience working on. And basically, without getting into the details of the numbers of this chart, the goal is to achieve state-of-the-art performance, but with strong limitations on the number of labeled examples you get. So everything you see after the @ sign is the number of labels that you have available to you. The detailed specific numbers will come to you once the program starts. Okay, I'm going to skip the slide and just head to the schedule. So I mentioned this is a 3-year program. It is divided into 2 phases. There's a challenge problem at the end of each year. There's a series of annual evaluations where we on the government side curate a set of problems for you and a mechanism for you to retrieve the labels that you care about for each of these problems. And then your systems need to operate autonomously during these challenge problem evaluations. And your goal is to reach the target that we've stated for you. That's basically the program. This will end in hopefully a system or a series of algorithms and publications about those algorithms that is way more efficient than the algorithms that we have today and fully automatic. So what I'm going to do now is leave this open for questions. I think that you have question cards that you can write things down on. And I'm not sitting in front of the schedule right now, but Bridget may know what's coming up here next. But I believe there's some time for you guys to talk amongst yourselves, figure out how you might want to team with each other and work with each other in order to build proposals. Is that what's coming next? Okay. So with that, please write down your questions. We will collect them. We'll go back into the back of the room, answer them, come back and read these answers to you so that you get a coherent union of all of these things and responses. Thank you all.